I have to cut it later. Okay, the isomers, we talked about the constitutional isomers before, where you have and cis and trans isomers as well. When you have the connectivity for the atoms is different. You have constitutional isomers. You have like 4-carbon straight carbon chain, versus if you have a 4-carbon but not in straight chain, you have these two isomers. These are constitutional isomers. We talk about the geometrical isomers. In geometrical isomers, you have the connectivity is the same, but arrangement in the space is different. So when you have carbon-carbon double bond, that's one of the examples for geometrical isomers. You have carbon-carbon double bond, you have two groups. If the group, the two heavy groups or high priority groups, if they are on the opposite side of the carbon-carbon double bond, is called trans. And if the two groups are on the, or two same priority groups, they are on the same side, is known as cis isomers. So we do have cis and trans isomerization based on the geometry or arrangement in the space, even though the connectivity is the same. For cycloalkane, also, if the groups, they were on the same side of the plane of the molecule, then it's called cis. Like the bromine and chlorine, they are both coming toward us. Or they are in the same direction, is cis. And if bromine and chlorine, which are the high priority groups, they are in opposite side, is known as trans. So we do have other examples of cis and trans for cyclo, like this cyclohexane example that we have here. The new type of isomerization, where we have pair of enantiomers. Pair of enantiomers, those are molecules that they are mirror image of each other and they are not superimposable. So for compound to have chirality or to have pair of enantiomer or its mirror image as the enantiomer, one of the condition is that it should be a chiral compound. Chirality or handedness, that means that these compounds, they are mirror image of each other, but they are not superimposable. If you have a chiral compound, like this compound, this glass is achiral. If you try to match the two images, you overlap these. If you were just magically could bring one glass over the other one, is going to superimpose. When you talk about the handedness or the chirality, like if you hold these two hands and try to superimpose it, it's not going to cover. So you have chirality or handedness when you try to superimpose it, it doesn't overlap or superimpose. That's one condition. Also, if you rotate one molecule by 180 degrees and try to superimpose, still it doesn't overlap or superimpose. So if the two molecule meets the condition, then it's going to be like mirror image of each other. And if they are non-superimposable, it's a pair of enantiomers. If they are objects that they have superimposable mirror image, those are called achiral, and the others that they are non-superimposable mirror images, those compounds, they are chiral. There you have the chiral molecule. So chirality is again just you have the compound and its mirror image. It's not superimposing. So you have these the hands that you have here. These are chiral compound, and then you have superimposables that these are not chiral. If the molecule is chiral, most likely there is no plane of symmetry. Let's say if you try to cut the molecule in half, the left and right side of the molecule is not going to be the same if you have a vertical line or if you have a horizontal line, the bottom and the top part of the molecule is not the same. But if you cut this fork in half, like for the best estimate, the left and the right side of the molecule is going to be alike. So if the molecule has plane of symmetry, then the compound with its mirror image is going to be superimposable. So the right hand, the left hand is not superimposed, but if you bring these two forks, you see that they are superimposed. If we move to these molecules, one condition for molecule to be chiral is to have like a chiral center. You do have, this is like general, you do have some exceptions, and that you could have like a molecule that is chiral, but it doesn't have a chiral center, but that would be like a bulky compound, and we are going to talk about those exceptions. And then you do have a compound that has chiral center or more than one chiral center and is not a chiral compound. So let's cover the general definitions first. If you have a center that is attached to four completely different group, this center is called a chiral center. So we do have a chiral center, and for a tetrahedral atom bonded to four different group is going to be chiral center. So if the molecule is chiral, the molecule and its mirror image is not superimposable, then you have pair of enantiomers. Examples of a chiral center. See, for 4-octanol, you have a hydrogen attached here. That's one group. You have OH group attached. You have butyl group attached in one side, and you have propyl group on the other side. The group on the left and right, even though they are both alkyl group, but since one is 3, the other one is 4 group, 4 carbon in the chain, that they are not the same. So we have 4 different group attached to it, and we do have one chiral center. And the same for the molecule of 2-bromobutane, you have a hydrogen, bromine, and you have ethyl group with methyl group. So the molecule contains a chiral center. See, the groups attached, they are different for carbon number. If you come from the right to left for carbon number 3, or from left to right is going to be carbon number 1, 2, 3, 4, the carbon 4. And also for carbon 2, what happens in carbon 2? Can you tell me if carbon 2 is chiral or not chiral? You can use the chat, or you could use Mike to respond. Is carbon 2 chiral or not chiral?
Not chiral.
Not chiral. What makes it not to be chiral is that you have 2 of the methyl groups are the same. So in order for a molecule or center to be chiral center, all 4 groups must be different. In this case, you have a hydrogen, you have this, let's say, isopentyl group, and then you have the 2 methyl groups. Since the 2 methyl group are alike, the center in carbon 2 is not chiral center. And so we have only one chiral. Recognizing chiral center is the first step, because then based on that, you have to name and number and all the other good stuff that we learn in this chapter.
Professor?
Yes.
That last slide, so what can make that that molecule chiral, if you go back real quick?
Which one?
The 2,4-dimethylhexane. So what would make that chiral?
This is a chiral center. So we do have, it's chiral, but we have only one chiral center. So this is chiral. But if in this case, like if you had like a CH3, CH2, you would have 2 chiral center. So you already have one chiral center and it is chiral molecule, but I'm saying you only have one chiral center. Is this molecule, is this carbon here chiral or not? Then that's another, just a question. Is this carbon chiral or not chiral? Like carbon number 3 here, is it chiral or not? In order for carbon 3 to be chiral, it must have 4 different groups attached to it. Since 2 of the groups are hydrogen and they are identical, so that makes carbon 3 to be not chiral for 2-bromobutane. In 2-bromobutane, only carbon 2 is chiral and carbon 3 is not chiral. Sometimes it's good to practice with the centers that are not chiral. So just to see the difference, like how would it look like if it's chiral, or what makes it the achiral center.
Excuse me, Professor, is the second carbon in the 2,4-dimethylhexane, is that sp2 hybridized?
Second carbon here. Oops.
Yes.
No, it is sp3 actually.
It is sp3?
It is sp3 because it's attached to 4 bonds and there is no double bond there. If the carbon had double bond, or carried 1 double bond, then it would have been sp2. But in this case, because there are 4 groups attached to it, is going to be sp3. It's just that the 4 groups are not 4 different groups. 2 of them are the same. The CH3s are the same. So this carbon is not chiral, it's achiral.
I'm not seeing how the other carbon is chiral than the 4th one.
This one?
Yeah.
Okay. Can you tell me what's the first group attached to carbon 4?
You have a hydrogen, you have 2.
Hydrogen, okay. One
have
is
2.
hydrogen, and the second one is a
You got 3 carbons, I believe.
ethyl group, right? Then
Yeah,
you have
one
a
methyl.
CH2CH3, that's the ethyl group. And then the other one is a group with like a isobutyl group, right?
Okay, yeah.
So it's four different groups attached. So it's because you have 4 different groups is going to make it chiral. So it's good to practice actually with the molecule and see why the other one is not chiral and this one is chiral. And if it's hard to see it, it just lists the groups that are attached to that carbon and number them so you could see it better. It's the first time or first, part of the chapter. So it does require some, detailed practice. Okay. For this molecule, for the enantiomers, so if we have the compound and the mirror image, if they are not superimposable, then we have pair of enantiomers. Pair of enantiomers, they have same molar mass. They have same polarity. So the polarity is the same because the dipole moment is the same. The connectivity is the same. So they should have same melting point, boiling point. They are very similar in every aspect of physical and chemical property with like one minor change. One is that the physical property that they are different, which is going to be covered the second half of the chapter or toward like a slide number 18 to 20, is the rotation of the light, plane polarized light. If one rotates to the right side, the other one would rotate to the left side. I will explain that aspect again later on, but there is a point of difference. And if there is a point of difference, then we should name these 2 compounds differently. So if we have 2 different compounds, they should be named differently. And in order to name differently for a chiral compound, the chiral center is going to be named as either S or R configuration. So we have like 2 different names for the compound because they have at least 1 point of difference. So when you are drawing the structure for this molecule that we know 2-bromobutane is a chiral compound because it has a 1 chiral center, we would draw like 2 dashed line for 2 of the group and they must be adjacent. They cannot be separated from each other. And then the other 2 groups attached to, one would be like you're using dash line and the other one with the solid wedges. So you have the dashed or and sulfurs. And then you look at you would draw the mirror image for this molecule. So if you look at another example here, is that the same? So you have your other two molecules that these are, if they are chiral, then the mirror image is not superimposing. If it's achiral, then the mirror image is going to be superimposable. You can rotate the molecule by 180 degrees, as I showed with my examples of my hands. So if you rotate this like by 180 degrees, this molecule can go overlap the CH3, CH3, Br, Br, and then these CH3, these groups are going to overlap. This is a superimposable. If it's achiral, they are superimposable. Sometimes it's easier to just look at it if it's a chiral compound and then draw the compound with the mirror image. Try to like slide it over, just like the sliding of the hand over the other hand or the fork over the other fork, to see, just imagine if it was like slide it over, would it be superimposing, would it cover or would not cover it. So still definitions for the mirror images. Okay. So when you are drawing the mirror image, two of the bonds that are adjacent, two adjacent bond is going to be used, like the plain just dashed line, and those are the bonds that drawn on the plane of the paper. One group going away from you and one group coming toward you. So that's how you draw for the 3D structures.
Professor, could you please repeat about the chiral and achiral molecules? Like what is the example? How do they arrange in space in a manner that they're not superimposable?
Okay, if you look at the molecules if you look at the definitions for chiral compound, 4 different group attached to it, okay? Like this example that we have, you have group hydrogen, bromine, CH3, and ethyl group. That's the chiral molecule, and it has its mirror image that if you try to shift this over, this carbon over this carbon, bromine is going to overlap, right? Bromine would go over, and then hydrogen would come here, but ethyl group is going to be here. So it's not going to superimpose it. It's not going to cover each other. And that is the chiral center. And the other way just to look at it is if you have molecule that has 2 same group, you don't have a chiral center, because condition for chirality is like all these groups should be different. You have 2 groups that they are the same. So this molecule is not chiral. You don't even have to draw the mirror image. If you take that definition, it's going to make it easier. Okay, so it's not superimposing. It is superimposable, or it's not chiral to begin with. This is an achiral compound. Okay, it's an achiral compound.
So in order for us to know if it's chiral or achiral, we do not move the molecule. We do the mirror image, and then if they do not superimpose without moving, then we know it's not chiral.
Yes, and also that you must see the chiral center. Determining the chiral center is the first step, and that makes it kind of easier, because if you have a molecule that you have 2 similar group attached to it, it's achiral, and that's out of discussion, so you don't have to do anything else with it. Like water molecule, you draw water molecule. Is this chiral or achiral center?
Achiral?
Chiral?
Achiral, because you have 2 groups that are the same. Or another way of saying it is that you have, if you cut the molecule in half, you have 2 exact same. There's a plane of symmetry. So if you see plane of symmetry, your molecule is achiral. If you have 2 groups that are similar attached to the center, then it's a chiral molecule. So you don't have a lot of chiral centers. You just, the chiral centers are very rare, but they do exist. And if the molecule that you have with the chiral center that has 4 different groups attached to it, or there is no plane of symmetry, then we know that is a chiral compound. And if it's chiral and it has a chiral center and it doesn't superimpose the mirror image, it's going to be chiral compound. Okay. Now, if you have a chiral compound, that means that compound with the mirror image is not superimposable, even though the compound with the mirror image is going to have very similar physical property, but still those are 2 different compounds. And since they are different compounds, then we have to name them differently. How would you name these 2 compounds differently? Because both of them are 2-bromobutane. Okay, to name these 2 compounds differently, both of them are 2-bromobutane, so you just have to add a designation to it. And this one, if we name it, is a 2-bromobutane. Based on everything that you know before chapter 5, these 2 compounds are the same, right? But they are not the same because one would rotate the plane polarized light to the right side, the other one to the left side. So we have to name it differently. These 2 compounds are not the same because if they were the same, they would be superimposing. And since they are not the same, we have to name it differently. In order to name these compounds differently, you give priority to groups. So these are the kind of steps. So before giving the R and S configuration, did you get the steps how to determine if the center is chiral or not? Just one more time.
Yeah, we got it.
Good, perfect. So now, if you know that your compound is a chiral compound, then you want to know, is it S or R? So R configuration, S configuration. In order to do that, you have to give priority to the 4 groups attached to it. And priority goes with the first element attached to from the group attached to the chiral center. The higher the atomic mass, the greater the priority, or the higher the priority. So we give like priority 1. So we are going to compare. If you have hydrogen, you don't have any group that weighs less than 1, right? Hydrogen, and then it goes to CH3. So hydrogen always has the lowest priority. So we can, as soon as you see hydrogen as one of the group, we can say 4. Okay, then you have 3 to compare. You have bromine, carbon, and carbon. Which one takes higher priority? Which one has higher atomic mass? Bromine, carbon, or carbon?
Bromine?
Bromine?
Bromine has higher priority, so we give priority 1 to bromine. Second, we have carbon and carbon, so we cannot decide based on carbon and carbon because carbon has atomic mass of 4 and this 12, and the other carbon also has atomic mass of 12. So we have to move 1 bond further. If we move 1 bond further on the methyl group, we reach to hydrogen. We move 1 bond further in ethyl group, we reach to another carbon. So ethyl group is going to take higher priority compared to methyl group. So this priority is going to be 2, and I circle the priorities, and methyl group is going to be priority 3. So you have assigned the priority on the for the molecule on the right side now. And next step would be to start with the priority 1 and move clockwise or counterclockwise, going from high priority to low priority. So you can go from 1 to 2 to 3, and then say, is this clockwise or counterclockwise? For a 3D molecule, this, when you have clockwise is going to be R, moving clockwise would be R, moving counterclockwise is going to be S. This is moving counterclockwise, so it would be S. And if this one is S, the enantiomer or the mirror image of this molecule is going to be R, but let's try it first. So what we are going to do here, we are going to add the designation of S to this molecule. So is S2-bromobutane. So if you look at the other molecule, give the priority. I'm just going to give the priorities just like the other one. Hydrogen would take the highest priority, which is, I'm sorry, highest number, which is the lowest priority, that's 4. Bromine is 1, and then between methyl and ethyl, we have 2 and 3. Okay, so in this case, you are going from, I'm sorry, I moved clockwise here and I numbered it S. So this is clockwise. You can correct me. I moved too far. So that was a clockwise actually. So we had R here. And for this one, we are going from 1 to 2 to 3. 1 to 2 to 3. This is counterclockwise. And since is like a left turn is going to be S. Left turn would be S, or counterclockwise would be S. Right turn or clockwise is going to be R. I kind of lost my R, the right and left for a minute. Okay, so the right turn for R, left turn for S. So this molecule is going to be designated as S molecule. Now, there is some limitation. If you are going from priority 1 to priority 2, you can pass by 4, but you cannot pass by 3. Okay, so you must go from the side that you don't pass 3. So you can go from 1 to 2, pass by 4, but you cannot go 1 to 2, pass by 3. So that's the limitation. So you have to be careful with that when you are going from high priority to low priority. You cannot get the other priorities. You cannot pass the other priorities except priority 4.
Professor,
So
I got a question.
yes.
Okay, so for example, you're saying that it's based on the atomic mass. So for example, we have a hydroxyl group, which is the oxygen plus the hydrogen. So
The first group, the first atom attached to it. So you don't count the hydroxy group, you count the oxygen.
okay. And if I have an oxygen and a ethyl group, so which one will be higher right there? Because the oxygen will have, it is
Oxygen
16,
would
right?
be, oxygen is 16 and carbon is 12. So oxygen would have higher priority.
Oh, okay. So we only count the 16 and the 12. We don't count the 12
No.
and the other 12 of them.
Yes, yes. You don't
Oh.
count the 29 and 17. You count the 16 and the 12.
Oh,
And
okay.
if you have two groups that both of them, the first atom is 12 and 12, then you move one bond further away. We will have more examples, but at least you know that it's based on the atomic number or atomic mass of the first element attached or directly bonded to the carbon with the priority group. Okay, so we are starting from the first atom attached to it, the atomic number. If you get to tight position, then you move for bond away, further away. Okay, so if the priority group is going clockwise, let me do this. Okay, if we had these the priorities were assigned to be like this, and this doesn't have the actual number, it's just the example. If you had the priority 1, then 2, 3, and 4, going from 1 to 2, if it's clockwise, is going to be R. If it's counterclockwise, it's going to be S. Okay? So if it's counterclockwise or going to the left, it's going to be S. Okay, 2-bromo-butane again, the example. The arrangement, is it R or S? Let's practice again. It's the same molecule. Let's practice. You have priority 1. Now, everyone should know why this is priority 1. That's priority 2, priority 3, and priority 4, right? Bromine has the highest atomic mass or atomic number. Hydrogen has the lowest atomic number. Between the carbon and carbon, they are the same. So I have to move one bond away and go for hydrogen and compare here to the carbon. This carbon is attached to another carbon, but the carbon and methyl group is attached to only hydrogens. So the priority goes with the ethyl group compared to the methyl group. And since this rotation is a clockwise rotation or going to the right turn is going to be R. Right turn, R, and left turn is going to be S. Let's try the other one to see if it's actually left turn or not. We have one ethyl group, we already know, already had enough practices. The ethyl group compared to methyl group, ethyl would be 2 and methyl would be 3. Hydrogen is 4.
So that'll be S.
And this would be S. Very good. So it's just like a step. You have to take one step at a time, try to find the priority, and then just move from high priority to low priority to see it's moving clockwise or counterclockwise.
Professor, does the S or R go into the naming of the
Yes.
compound?
Yes, that.
Oh,
that
I see it
shows-
there.
Yes, that shows the name of the compound. So we have to, before chapter 5, as I said, we would just name these 2-bromobutane. But now we have to name them differently because they have at least one physical property that they are different. So they must have different name. I mean, for 2-bromobutane may not be like a big deal. Is it R or S? But I don't know, you have heard, or you can search for it, like thalidomide. Thalidomide in 1960s was used for morning sickness, to cure morning sickness. And then there were like many babies born with the birth defect, with like short arms or short hands. And they found out that was the side effect of the medicine, the thalidomide that they were using for the morning sickness. So they did stop, and then further research showed that only one of the enantiomer has that effect. The other enantiomer is actually safe. You would also learn in lab, or like when you do experiments for resolution, experiment 7, that it's very hard to separate these two with 100% pure into 100% pure compound. As a result, they have to be very, very careful. So another medicine that is used for Parkinson's disease, one of the enantiomer, either R or S, is effective for the Parkinson's disease, and they just say that the other one is not giving any side effect and is okay. But who knows, in years from now, they will find out that whoever had like a brain stroke is because of the other part, the mirror image of that compound, that it should have not been consumed, and they have to be like very careful. Prior to 2013, FDA, they didn't even make the manufacturers of the pharmaceutical companies to label the percent purity of the R and S. They would tell you, just go take Tylenol, right? And then when they take the instruction actually says, take Tylenol, take as needed for pain. Do not take more than, how many? Is it like 8 in 24 hours? But you could take 1 or 2. It doesn't say exactly how much to take because they know that part of that Tylenol is the R Tylenol and the other part is like S Tylenol. So far, there is no research that's showing that the other one is damaging or it has like severe side effect for people. And they just say that it will not stay in the body. It will be safe. It is safe, and we are using Tylenol left and right. But who knows what is the side effect of the other one? At least it's not proven yet, and we have to trust the scientists. And then we just say that. But if you look at the instructions, like for amoxicillin, they just say, okay, take one pill or 1 capsule every 8 hours because it's not a chiral compound. There is another problem, since we're talking about the medicines, that if it has a chiral, if it has an enantiomer, over the time, like maybe 2 years, 3 years, the S enantiomer can change to R enantiomer and vice versa. So if it has the shelf life of 2 years and says that it expires after 2 years, basically there's a possibility that the effective enantiomer has been lowered in the concentration, is not that effective, and sometimes is not safe to take it. But that's like something that and they have to do more investigation to find out exact shelf life and at what point it's poisonous to take the expired medication. So since these compounds, they are different, going back to the naming, they must be named differently. So if we have the R enantiomer and S enantiomer, we have to name it differently. And it does make a difference. And the only difference that we have is see that all the groups are the same. It's just the arrangement in the space is different in a way that if you go from priority 1 to 2, and if it's clockwise, it's going to be R, and if it's counterclockwise, it's going to be S. Okay. Switching the priority or the group that they have like different priority. If you to look at the configuration, what would be the configuration for this molecule now, based on going from 1 to 2 to 3? So it's moving clockwise or counterclockwise? It's like a right turn.
Clockwise.
Right? So it's going to be R. Now, if you switch these two, okay, if you switch it, it's going to be 1, 2, 3, and it's going to be, if it's switched in a way that the lowest priority goes away from you, and you had to switch that, then it's going to be the lowest priority group must be away from you. So if it's not away from you, if it's facing you, if it's coming toward you, you have to switch the configuration. So automatically becomes like the opposite. That part, let's just go back here. It's showing more clear here. For these molecules, the hydrogen, which has the lowest priority, is going away from you. Okay, and the hydrogen here is going away from you. So just keep in mind, the clockwise and counterclockwise is meaningful when you have the hydrogen going away from you for the being R, when it's right turn, and left turn would be S. Now, if the hydrogen is coming toward you, is not going away from you, if it's switched with the other priority group, then the configuration is going to change. And that's like, we have like a Fisher projection. Then for the Fisher projection, which you learn soon, is going to be hydrogens are coming toward us, so we have to switch the configuration. It's going to be opposite. R would be S, S would be R. So for this molecule, that's where we're talking, since the hydrogen is not going away, clockwise means S, counterclockwise would be R.
The only way we would be able to tell that is to have both enantiomers, right?
Or if you have the 3D structure, yes, you must have the 3D structure.
But of both
If you
of
have
them,
a
right?
3D structure, it would show you if the hydrogen is on the dashed line or is on the solid triangle. If it's on the dashed line, that means it's going away from you.
Right, but in the
Or the
second one, you
3D
have the hydrogen on the dash line. If they just gave that one to you, you wouldn't switch it, right? S and R?
Yes, if that was the case, then you don't switch it now.
Okay,
Very good, very good. So if H hydrogen is in the dashed line, you don't switch it. And then you just look for the priority if it's going clockwise or counterclockwise.
So it's only if the hydrogen is in the wedge position. Is that correct?
Yes,
Okay.
yes. If it's not, you have to switch it, and then you also have to switch your rule. If you end up switching to make the hydrogen to go to wedges, then you have to also switch your rule and say the counterclockwise would be R. Because you had to switch it.
Seems like the molecules can't make up their mind, Professor.
Okay. And you could argue that, you could say, why these molecules are behaving this way and why do I have to learn this? And then when you see a real life example of a thalidomide that's causing so much of trouble and having babies born with like a short arm just because of this, with the birth defect, then becomes like important. So we have to pay attention. That little thing, that hydrogen is in the back or is in the front, it makes a huge difference in the life of someone, an unborn baby. You're right. It could have been simpler if they all had their mind set just to be one form, not the mirror image. When you are drawing arrow sign, I said earlier that you cannot bypass priority 3, but you could pass the priority 4. Okay, you could pass the lowest priority, but never pass the group with the next lowest priority. So you could pass 4, but you cannot pass 3. It makes the rules more specific. Okay, let's see what we can find out here and about the molecule. Do we have a pair of enantiomer here? Are these pair of enantiomers or not? How
I
should we
believe not.
find out if these are pair of enantiomers? How I'm going to switch it around to see if these are mirror image or not? Sometimes it's harder for you to have like a 3D imagination and 3D picture in your mind. If I switch it around, would it overlap? Would it superimpose or not? It would be easier since you already learned how to determine the configuration. If you determine the configuration if this is hypothetical, okay, if you determine this to be like S configuration and also this one S, then you would say these are two same compounds. If this one is S and this one is R, then you know these two are pair of enantiomers. Okay, if one enantiomer is S, the mirror image is going to be opposite. It would be R. If both of them are S, then they are same compounds. So let's start working on this first or the structure on the left side because it's easier. Hydrogen is already in the right position, and you give the priority 1, priority 2, 3, and 4. Any questions about the priorities, assigning priorities?
No.
No. Now, next step we go from priority 1 to 2 to 3, right? And this is going to be clockwise or counterclockwise?
Counterclockwise.
Counterclockwise. And since hydrogen is going away, it's going to be counterclockwise would be S.
S.
Okay. So generally, or the rule is the hydrogen should go away from you. And if it goes away from you, counterclockwise would be S, clockwise would be R. If it's the opposite, now if we have a situation that hydrogen is coming toward us, then you have to switch to position, but instead of the switching position, switch the rule and say, since hydrogen is coming toward us, is in the solid triangle, then is the rule is going to change. We don't know this is R or not yet. I just said, if this is the enantiomer, it would be, if it's the mirror image is going to be R. So we already know this one is S for sure. So for the molecule on the right, let's assign priority. We have priority 1 for oxygen. Everybody should agree with that. If not, let me know. I could pause and you can think about it. This is a priority 2. Hydrogen is a priority 4, and methyl is priority 3. Now, we are going from priority 1 to 2. Okay, going priority 1 to 2. Is this clockwise or counterclockwise?
Counter.
Counterclockwise.
Counterclockwise. If it's counterclockwise, the first thing you're going to say, you would say it's S. But you may want to pause and say, okay, it would have been S if hydrogen was going away. Now that hydrogen is coming toward, counterclockwise becomes R, right?
Yes.
Okay. Now, because the molecule on the left side is S and the molecule on the right side is R, these two molecules are pair of enantiomers. Even though if you place a mirror here, it doesn't show that they are mirror image, but that's how they are drawn. That a second way of finding out they are mirror image, rather than just bringing it together and trying to match, is to determine the configuration. If it's S and R, then, and you did determine the configuration properly, they are pair of enantiomers. Very good.
Professor, question. Is it the same thing if you rotate the bottom of the molecule, or it doesn't have the same outcome?
Okay, if you rotate, does it mean that you would rotate it by 90 or 180?
I mean, I will put the methyl group where the propyl group it is, and then the H is gonna go to where the methyl group is. So like if I rotate
even if you do that, okay, even if you do that, because the top of the molecule, you have the OH and you have a CH3 here, is not going to look like that they are mirror image. But this is just, I think this would be easier to determine the configuration. And if they are opposite, they are pair of enantiomers. Now you have to switch more than one in order to be able to see that they are mirror image, right? Because if you just switch to 3 and 2, it doesn't show that, because you still have the OH and this one not facing each other. This is the case that you don't see them. It's not easy to visually determine they are mirror image. Then you just do configuration first. And if the configuration is the same compound. If the configuration is opposite, it's pair of enantiomer. They are mirror image of each other. Okay, this part, if you have the molecule already and you're trying to draw the structure desired with desired configuration, you have to pay attention to these steps. Okay, so if you know that this molecule is a S-alanine, okay, is amino acid, and we know that is S. What should be, how should I draw this structure? First of all, you determine the chiral center, because if it says S only, that means you only have one chiral center. The groups are, the chiral center, I could say, is this carbon, right? Because you have a NH3 group, you have CH3 group, you have COOH, and you have a hydrogen group, 4 different groups attached to it. So you would draw your central atom or the chiral center first. You draw 2 of the group in the plane of the molecule. And if you want to draw it plane of the molecule, you would draw dashed lines. Okay, so dash line. And you would draw this wedges and dashed. So you have the hashed or solid. Okay. Now, the next step for me, okay, put 2 of the, you can put 2 of the groups, okay. Planar must be adjacent to one another. So these 2 must be adjacent to one another. So you can either draw this or you can draw this. One or the other, either one. Okay, you cannot do a straight line and line here. It has to be adjacent. And then you're going to put the lowest priority group in the hash wedge, right? That, because you want to make sure that the clockwise, at least this way, you know, the clockwise is going to be R and counterclockwise is going to be S. And because we wanted S, what should happen next? What would be the next step? I would draw a circle here and going from high priority to low priority, going to counterclockwise because I want to make it S. Because I want to make this S enantiomer.
So the COO would go on the left side.
Now let's assign the priority, because we don't know, we already know that priority 1, I'm sorry, lowest priority hydrogen with the lowest priority is already is clear. Between the others, we have to decide which one takes the highest priority. We have a CH3, we have NH3, and we have a COOH. Which one has the highest? Which one has the highest atomic number? Nitrogen or carbon?
Nitrogen.
Nitrogen.
Nitrogen has the highest. Okay, so this would be 1. Sorry, you know, we have to have good orientation working with this. Has to go clear, arrow, and then ink. Okay, nitrogen has high priority. That's 1. We have hydrogen 4. Between CH3 and COOH, which one is 2, which one is 3?
The methyl group is your 3.
Methyl group is 3, and this is 2. So the point of this practice is you draw your carbon with the 4 groups first, and your very next step, and then if you have a hydrogen, put the hydrogen, or anything with the lowest priority group, put in the dashed wedges here. Then draw the line or draw the arrow. This is a counterclockwise because hydrogen is going away from you and it is S. Now you know that if you put 1, 2, and 3 here, it's going to be S. Okay, so then you determine the groups. But if you draw this molecule and say, okay, I'm going to put the CH3 here and then hydrogen here, it would be hard to rearrange these. How we are going to do rearrangement. This is just showing the easiest step. You might get right, but if you follow these steps, you can't go wrong. If you follow the steps correctly, you cannot go wrong. Then you put the high priority to low priority because you already know which direction it should go. You already have the 4 down, and then you put the nitrogen. You have your nitrogen, and from nitrogen, because it's counterclockwise going to the COOH, then you put your COOO here, COO minus. That's a carboxyl group, is amino acid, and then CH3. So you put your carbon skeleton, you draw the 2 dash line, 1 hatched, 1 wedged, and then you would do lowest priority group in the hashed area, and then you would do you put the groups. Determine the priority of the group before you bring in. Okay, this projection or the structure that we have when the crust line is used, if your molecule has 1 chiral center, you just put the 1 cross line with one crossing point. Okay, if your molecule has 2 chiral center, you would draw 2 horizontal line with 1 vertical line, and each of these cross points would show a chiral center. If your molecule has only 1, then you only need 2 lines, which is 1 vertical, 1 horizontal line. It's much easier to see the mirror image when you have your Fisher projection. By convention, they say groups that they are in the vertical line, they go away from you. Groups on the horizontal position, they come toward you. I'm going to repeat one more time. The groups on the vertical line, they go away from you. Groups on horizontal line, they come toward you. So for this structure, a clockwise would be R or S. And a counterclockwise would be R or S if it's a counterclockwise.
Counterclockwise is S.
Counterclockwise, it would have been S, but I said first that this is coming toward us. Anything on the horizontal line is coming toward us. Hydrogen is coming toward us.
Oh, so
And
it's
because
an R.
hydrogen, so you have to switch it around, right? So you have to switch the rule.
Yeah, you have to switch it.
You have to switch the rule. So, is this clockwise or counterclockwise? What do we need to do? What are the steps? First step would be to determine the priority. So we have 4, 1, 2, and 3. Okay, we know this hydrogen is coming toward us. So if it's clockwise would be S, if it's counterclockwise would be R. Going from 1 to 2 to 3. So it has to go this way, and that is left turn, so it would be counterclockwise. And if it's counterclockwise, it's going to be R. For the structure on the right side, what is the configuration for this one? R or S, or do we have to determine it? Do we know already this is R or S, or we have to determine the priority?
I think you would determine it, right?
Are those 2 pair of enantiomers? Are they pair of enantiomers?
Yes.
Yes, they are mirror image, right?
Then it's
And
S.
if one mirror image is R, what is the other one?
S.
Yes. Okay.
Okay, this is very clear that they are mirror image. And if one is R, the other one is S, you don't have to determine it.
It's harder to tell though without the wedge or the dash line for the H.
Okay, if you place a mirror here, if you place a mirror here,
Okay.
and the
We'll
distance from
reflect
the
off each other.
hydrogen, see,
Okay.
it's like, it's clear that this is the mirror image.
Yeah.
So because it's mirror image, and if you try to superimpose it, it's not superimposing, because hydrogen would overlap with bromine and bromine would overlap with this hydrogen. So it's not superimposing, it's going to, it is mirror image. And since these are mirror images, if one is R, that's my point. If one is R, the other one is going to be S, and you don't have to even determine it.
So you just determine one when it's symmetrical. Okay, I get it.
Just to be sure, you said that the horizontal is facing away from you, or was it towards you?
The vertical is away from you. This is going away from you, both of them. And then this is coming toward you.
So is the one on the left R because the H is on the
Is
facing
this
us?
clockwise or counterclockwise? First, tell me that. Going
That's kind of-
one to two to three. Is it clockwise or counterclockwise? The red
Counter.
color. Is this
Counter.
clockwise or counterclockwise?
Counterclockwise?
Counterclockwise. Is it R or S? Knowing that hydrogen is coming toward us. This is coming toward us. Okay.
How would you know that's coming towards you though, if it's just lines like that normally?
Okay. In
the
Fisher
horizontal-
projection, anything that is on the horizontal line, it comes toward us. And then anything on the vertical line would go away.
Okay, I got it.
Oh, okay.
Okay. Just a couple more examples. The high priority and this set, I mean, this, if the group with the lowest priority are on the vertical bond, okay, clockwise would be R. That means if it's on the vertical line, that means it's going away from us. So clockwise would be R. Okay. So if the lowest priority is on the vertical line, clockwise would be R, counterclockwise would be S. If the low priority group is on the horizontal line, then clockwise would be the opposite. Clockwise would be S, counterclockwise would be R. So if it's on the vertical line, that means it's coming toward you. So you have to switch it. But if it's on the in the horizontal line, like this one, is coming toward you. If it's on the vertical line, it's going away from you. Okay.
Professor, if the lowest priority, does it always have to be hydrogen in order for the S and R to flip? Or is it just the lowest priority, whatever it is?
The lowest priority.
Okay.
The lowest priority.
Usually hydrogen is always going to be the lowest. That's why they're
If
using
there is a
example.
hydrogen, yes.
Yeah.
Exactly. Yes.
That's why they're using an example, but they could throw something else in there to make it more tricky.
Mm-hmm.
Okay.
If they do that, it's going to be, let's say this is like a CH3 and this is a CH2 CH3. Still, this is going to be the lowest priority.
So they would do that if they're not nice people. They just want to mess with you.
Okay. And that's where I was planning to stop, and I don't want to bring the plane polarized, right? It's not hard, The other one, you probably be better off just, it was covered here, and you can sometimes look at your hand and says, oh, handedness, what does it mean? It doesn't superimpose. I mean, is it chiral, is achiral? When you have like a pen, if it's if you cut the pen in half, it's going to be, both sides is going to be exact the same, so it's not chiral. I mean, just fun activities that you could have.
Now I'm sleeping.
Okay, we are going to pause the